Hello everyone and welcome to CSEN 601 Computer System Architecture. My name is Walid Al-Hifni and today in this video, which is MIPS Datapath Single Cycle Part 2, I'm going to continue explaining the MIPS Datapath which I started in the previous video, Part 1, where I explained the single cycle implementation and gave an example of an R format instruction passing through the different stages of the data path. Today we are going to see the execution of three I format instructions: the add immediate, the load word and the store word, passing through the different data path stages, as well as solving exercises 2 and 3 from practice assignment 7. So now we will tackle the I format or I type instructions, and as you remember, the most famous I type instructions are the add immediate, like this one, the load word, the store word, and the branch unequal. So let's start with an add immediate instruction. And how does an add immediate instruction flow in our data path? We have here add immediate or add I, T1, S1, and 5. So as you can remember or you can recall, T1 is the RT or the target register, S1 is the RS or the source register, and 5 is an immediate or a constant number. And in the add immediate, the immediate field can take signed numbers. It can have a positive number or it can have a negative number. So it is signed, okay? What are we trying to do in this operation? We are trying to add the constant value of 5 to the value inside register S1 and store the result in register T1. And as you can remember, the I-type instruction or the I-type format is divided into 4 fields. We have here the opcode, which is 6 bits. We have the RS, which is 5 bits. We have the RT, which is 5 bits. And finally, we have the immediate or the offset, which is 16 bits. So if I want to decode or convert this instruction from assembly into machine code or binaries, I need to map it to these fields. So as you can remember, the opcode uniquely identifies an instruction, and every instruction in our instruction set architecture has a unique opcode, except the R format instructions. They all share the same opcode, which is 0, and using the function field we can differentiate between the multiple or the various R-type instructions. Okay, so since it's an I format, not an R format, so each I instruction will definitely have a different or a unique opcode. And then the RS will be what? Will be S1, the RT will be T1, and 5 will be the value of the immediate. So let's start. And the opcode, if we check the opcode for the add immediate instruction, we will find it is 8. And don't worry, in the exam you will be provided with a table of all instructions and their equivalent opcodes. So from this table, which will be given in the exam, you will know that the opcode of the add immediate instruction is 8. Now we need to convert 8 from decimal into binary. 8 is 1000, which is 4 bits. But the opcode field takes 6 bits. So we need to add zeros to the left so we can cover all 6 bits of the opcode. So that's why 8 is converted into 001000, because I need to fit the 8, the decimal value of 8, into 6 bits. But 8 is represented in only 4 bits, which is 1, 0, 0, and 0. So we need to add 2 zeros to the left so we can have a 6-bit representation. Okay? Followed by the RS. Register S1 is register number 17. As you can remember from the previous tutorial, you will have a table with the list of registers and their equivalent numbers. So S1 from this table is the register 17, and we need to convert the decimal value of 17 into binary, which will be 10001. They are 5 bits, that's why we will not add any more bits, because the field takes 5 bits and the converted value is actually 5 bits, so we are good. So now moving on to the RT, we have that the register RT is register T1, which is equivalent to register 9. From the table we will find that T1 is register number 9. 9, to convert 9 from decimal into binary, it will be 1001, which is 4 bits. That's why we added a 0 to the left to make it 5 bits, because the RT field is 5 bits, and 9 to convert it to binary is only, or requires only 4 bits. So to fill in all 5 bits, I need to add a 0 to the left. Okay? Finally, the immediate, which is positive 5, is actually, when we convert 5 from decimal into binary, it will be 101, which only requires 3 bits. But the immediate field takes 16 bits. That's why we added what? We added the remaining 16 bits as zeros. So actually, I have 3 bits here that represent 5, which are 101, and the remaining 13 bits are added as zeros to fill in this immediate field, which requires, or which takes 16 bits. And you need to take care about this. You need to preserve the number of bits required for each field. If the conversion took less, I need to add zeros to the left to maintain the number of bits required in each field. So finally, we will have this instruction. This is the assembly instruction, and this is the equivalent machine code or binary format. The opcode 001000 identifies that it is an add I instruction. The RS, which is S1, is represented as 10001. The RT, which is T1, is represented as 01001. And finally, the number, or the immediate, or the constant value of 5 is represented as 13 zeros and then 101 to take all 16 bits. Okay? Then we will concatenate all of these together to form the equivalent machine code of this instruction, or of this add immediate instruction. So as you can see here, this blue box contains the instruction concatenated, which will flow in our data path. And as you can remember, this image or this diagram, this is our simple implementation, or this is the simple implementation of the MIPS data path. So let's trace it from the beginning. And as you can remember, the first stage was the instruction fetch stage. If you cannot remember the stages, you can watch the previous tutorial on the video on demand platform, because I will not recap on how does these elements or components or stages work. We will just start tracing how an instruction flows in this data path. So if you have any questions, you can watch the previous tutorial. Now, we have this PC register, or the program counter register, which contains the address of the next instruction I want to execute. So it's pointing to an instruction in the instruction memory. The instruction memory contains all of our instructions, but we want here to execute which instruction? The add immediate instruction. So the program counter, or PC, will contain the address of the add immediate instruction, which I want to execute. So in the instruction fetch, I will fetch this instruction from the instruction memory, meaning I will get it from the instruction memory. So the PC will point to this instruction in the instruction memory, and now I will retrieve it or get it from the instruction memory. As I stated, the PC contains the address of the instruction, or the following instruction, or the next instruction I want to execute, and the next instruction I want to execute is this add immediate instruction. So my program counter is pointing to this instruction in the instruction memory. Now I need to retrieve this binary or machine code representation, and this binary or machine code representation resides inside the instruction memory, and it has an address, and the program counter knows the address of this instruction. So I will retrieve it or get it from the instruction memory, and that is the instruction fetch stage. I am fetching an instruction from the instruction memory. Then the next stage is the instruction decode stage. As you can see, I decoded my instruction into the multiple fields. And as you can remember, I told you the MIPS data path, or any data path, is a dummy data path. At this point in the data path, I do not know which instruction I am executing. I did not analyze the opcode and know which instruction I am executing. So I will assume that I am executing any of the 3 format instructions, and therefore, as you can see, I am dividing the instruction into multiple fields making all the different combinations I could have. So I will try to divide it into an R format, I will try to divide it into an I format, and I will try to divide it into a J format. Because at this point I do not know which instruction I am executing. So as you can see here, instruction bits 21 to 25 is what? 21 to 25 is RS. So bits 10001 will be flowing here. The second line, instruction bits from 16 to 20, 16 to 20 is the RT, which is 01001. So these two lines contain the register number here of RS and here of RT. Finally, the third line contains instruction 11 or bits from 11 to 15. But guess what? I'm executing an I format, not an R format. Why should I take bits from 11 to 15? As I told you, the Datapath does not know which instruction you are executing, and therefore will try to create or recreate this instruction in an R format too. So that's why, if you can remember from the previous tutorial, bits from 11 to 15 were the destination register or RD register bits. So the RD, if I find here bits from 11 to 15, which I guess 11 will be from here till 15, it will be what? 5 zeros, okay? So I retrieved 5 zeros from the instruction. Is this my destination register? No. Do I have a destination register called RD? No, my destination register is the RT or the target, not the RD, because we are an I format, not an R format. So these bits are relevant, and whatever information they have, it will not continue further in the data path, because in the further stages, the data path will only allow the accurate data or the corresponding data of this instruction, because at that point in the future, it will analyze the opcode and know that no, I am not executing an R type, I'm executing an I type, so bits from 11 to 15 are useless for me. But at this stage, I do not know which instruction I am executing, and therefore I will take into consideration all different combinations, and I will try to map this instruction into an R, into an I, and into a J format. Okay, finally this line, which is bits or instruction bits from 0 to 15, contains what? The immediate value, which is this value, as you can see my cursor. So it tried to map it into an R format, it tried to map it into an I format, because bits from 0 to 15 only exist or are only relevant if you are an I format. If you are an R format, you will extract these bits, but they will not move further in the data path because they will be useless. So it's like the previous example we had in the previous tutorial. When we had an add instruction, we converted it into an RS, an RT, and an RD, and we tried to get an immediate or an offset. But this immediate and offset was dumped later on in the data path. Here, in an add immediate instruction, we tried to get the RS, the RT, and the immediate value, but also we tried to get the destination or RD. And we will not assume, actually what will happen is that this value will be dumped in the future of the data path. Okay, so here we try to do what? We got here the immediate value, which is number 5, okay, or the immediate value of 5. What happens in the instruction decode is that after we decode the instruction to all different possible formats, and take care the J format is not appearing here because this is a simple implementation, so it does not cover everything. But in reality, the instruction is decoded into all possible combinations and all possible formats. Okay, but here for simplicity, we only try to decode it into an R format and an I format. An R format having RS, RT, and RD, and an I format having RS, RT, and an immediate. And if you take care that the second part of the instruction decode is retrieving the register values from the register file. If you remember, the register file contains all of our 32 registers and their values. In a typical add immediate instruction, I only care about the value of RS, which is this line, because the value of RT is useless because I use RT as a target register, meaning I will store the result in this target register. So I do not need to read its value. But guess what? We are also in a dummy data path. So it will try here at read register 1 to read the value of register RS, and at read register 2 it will also try to read what? The value of RT. Also here in the add immediate instruction I do not need the value of RT, but guess what? As usual I will try to read it, and the values that will be output I will no longer use it in the rest of the data path. But since it's a dummy data path, it did not analyze the opcode, it decoded into all formats, so it will try to retrieve the value of RS and RT always, even if you are an I format and not an R format. So here we entered the register file, we try to retrieve the value of RS, and it will be outputted here in the read data 1 line, and we will also try to output the value of RT and output at register at line read data 2. Okay, so I decode the instruction and then read the values from the register file. Read the register values from the register file. Also, we can find here in the instruction decode stage that we have the sign extend module, which takes a 16-bit input and extends it to a 32-bit input or a 32-bit value. As I told you before, the sign extend module takes an input and tries to extend this input. In our case, it takes a 16-bit input and will try to extend it to make it 32 bits. Okay, and since it's a sign extend, meaning it will take into consideration the sign of the value, whether it is positive or negative. If it is 0 extend, it will not take into consideration the sign and will always assume it's unsigned and will add zeros to the left. But if it is a sign extend module like this one we are having in the data path, it will extend by 1 if it's a negative number or by 0 if it is a positive number. It checks on the most significant bit of the 16-bit value. If it is 1, it will add 16 ones to the left. If it is 0, it will add 16 zeros to the left. Okay, why do we have a sign extend module? As I told you before, for compatibility issues. I cannot, for example, add a 32-bit value, which is the default size of the registers and the size of the data we have in our architecture, to a 16-bit value. I need to make them aligned. So I need to add a 32-bit value to a 32-bit value. I cannot add a 32-bit value into what? Into a 16-bit value. Okay? So we are extending this immediate from 16 bits into 32 bits, and since the most significant bit, this one the cursor is pointing to, is 0, so I will extend 16 zeros to the left. Okay, now we finished what? We finished the instruction decode stage. We move on to the execute stage. We will perform the execution of the instruction, meaning if the instruction is an addition, I will perform the addition operation. If it is a subtraction, I will perform the subtraction operation. We have here the ALU, where the arithmetic logic unit, where all arithmetic operations occur inside this unit. It takes two inputs. The first input is always the value of register RS, which is from read data 1. The second input depends on what? On the instruction type. And now at this stage, we definitely knew the opcode was processed. And as you can remember, we have a control unit which does not appear in this graph or in this image. We have a control unit which takes in the opcode and releases all control signals. The control signals state what operations should be performed by, for example, the modules like the register file and the data memory, for example, or are acting as selection bits to the multiple multiplexers. And as you recall, the multiplexers act as gates. They allow one of the two values to pass. So which value I should let or which value I should pass depends on the selection bit. And this selection bit is given from the control unit. Okay, so you can see this multiplexer has a selection bit or a control signal called ALU SRC or ALU source. This will select one of two values, whether the value of register RT or the value from the sign extend module, which is the immediate value. Guess what? In an immediate instruction, do I need the value of register RT or do I need the value of the immediate Of course, you guys knew it. I need the value of the immediate because I'm performing an add immediate instruction or an add immediate operation. So what? I will take this value and will let it pass to the next stage. And as you remember, I told you unnecessary data or useless data that I retrieved because the data path is dummy will be dumped and ignored in future steps. This is one of the steps. I actually retrieved the value of register RT, but I do not need it in an add immediate instruction. And therefore, I have this multiplexer which acts as a gate and will only allow one of the two values to pass. And it will allow the value of what? Of the immediate or the sign extend module. That's why the ALU source will be 1 and one will select, this one will select the sign extend data or the immediate data and will not select what? The value of RT. And for your information, which we will take later, the control unit exists in the instruction decode in the previous stage. So you can imagine we have here a circle which has the control unit having the opcode from the instruction decode, because I will decode the instruction and we will take the first 6 bits from 26 to 31. We will have here like an imaginary line that enters to our control unit. The opcode will be processed and then the control signals will be sent to all components and multiplexers in our data path. So at the instruction decode, I'm actually still analyzing the opcode. So definitely at this stage, I do not know which instruction I am executing. But starting from the next stage, which is the execute stage, I know exactly which instruction I am executing. Okay? So here, what did we do? We took the input of register, or we took the value of register RS, we took the value of the immediate, and here at the arithmetic logic unit, we performed the addition operation. I'm adding the value of RS to immediate plus 5. And as you remember, the ALU takes control signals as an input, or not a control signal, it takes selection bits as an input to select which operation occurs inside the ALU. And we have here the ALU control unit, which will tell the ALU which instruction or which operation you need to perform. Should I perform an addition, a subtraction, an ORing, ANDing, whatever. Okay? And this ALU control will receive its control signal from the control unit, and at the same time, if it is an R-type format, it will need what? The function bits, and that's why we have here bits from 0 to 5 entering the ALU control. Just in case the instruction was an R-type, they all share the opcode, the same opcode, which is 0. Therefore, the control unit will not know which instruction you are trying to execute if it is an R-type format only from its opcode. So I need to have the function bits to help me, or to help the ALU control figure out which instruction or which R-type instruction you are using. So again, the ALU control takes a signal from the control unit, which is the ALU operation, and will tell the ALU here which operation to perform. The control unit takes as an input the opcode. So from the opcode, it will try to figure out which operation you are trying to perform. But all R-type operations have the same opcode, which is zeros. So I need to use the function bits from 0 to 5, which are the function bits in the R-type format instruction, to figure out which R-type instruction I'm trying to execute. And that's why the ALU control takes two inputs, takes an ALU operation and takes bits from 0 to 5, which in the case of an R format, it is the function bits, but in case of an I format, it is useless information. So yes, since it's a dummy data path, the ALU control will always take bits from 0 to 5, but later on, using this control signal, ALU operation, which come from the control unit, it will depend whether I will use this information to know which instruction I am executing, or I do not need this information and the ALU operation bits are sufficient to know which instruction I am executing. Okay? And as you can see, we're here in an add immediate instruction, and the add immediate have a unique opcode. Okay? So definitely the ALU control will not need the information from bits to 0 to 5 or the function information, and alone from the ALU operation will know that we are trying to perform an addition operation, and therefore will inform the ALU to perform an addition operation between the value of RS and the immediate value of 5. Okay, don't worry, in the next examples I will also explain the ALU control again. So if you did not get it fully from the add immediate instruction, you can get it from the next examples. Okay, just for now you should know the ALU control tells the ALU which instruction to perform, and it has an input signal from where? From the control unit, which we cannot see in this diagram, but we will see in later tutorials and lectures. So the control unit will send a signal called ALU operation to the ALU control, telling the ALU control which operations the ALU should perform, and this information is 100% gotten from the opcode that the control unit analyzed. But guess what? All R-type instructions have the same opcode, so I need to have a secondary data to help me figure out which instruction I need to perform in case I was an R-type instruction. That's why we have the function bits from 0 to 5 in an R-type instruction format. These bits will come handy or will help me if I am an R-type format to tell the ALU control which R-type instruction I am trying to execute. But if I am an immediate or a jump, I do not need these bits at all. They are only relative if I am what? An R-type format. Okay? Now the ALU control will perform an addition since we are an add immediate instruction, and will have two outputs. The first output is the 0 flag, which is a 1-bit flag indicating whether the result is 0 or not. If the result of the ALU operation is 0, this flag will output the value of 1. Otherwise, if the result is not equal to 0, this flag will output the value of 0. So if my value is 0, the 0 flag will be 1. If my value is not 0, the 0 flag will be what? 0. And we have here the ALU result, which is the actual result of our ALU operation, which is the add immediate operation. Now after we finish the execute stage, we will move on to what? The memory stage. In an add immediate instruction, we do not need the memory stage, but it will be performed resulting in useless data. Meaning that we have here the data memory. I am not a load or a store instruction, so I will not access what? The data memory. So here I have a line directly from the ALU result moving on to this multiplexer, and at the same time this multiplexer has an input from the data memory called read data. The read data will result in an high impedance state, for example, or an unknown data to me, because what? The data memory operates only if one of these two flags or two control signals is 1. Memory write, if it is 1, meaning I will write to the data memory. Memory read, if it is 1, meaning I will what? I will read from the data memory. Okay, if both control signals are 0, then I will not access the data memory. I will not perform any new operation. And these two control signals come from the control unit as the rest of all the control signals present in our data path. So we have here the ALU result, which acts as an address to the data memory, and we will see in future examples how this can act as an address to the data memory, especially in the load and store instructions. And then here I will have the read data line, which contains unknown data and unknown values that I do not care about. Why do I not care about? Because I have here the multiplexer, and this multiplexer will definitely take which value, the value coming from the read data or the value coming directly from the ALU result. As you all guessed correctly, the value coming directly from the ALU result, because we are performing an add immediate instruction or an add I instruction, and therefore this control signal mem to reg will come from the control unit and will tell this multiplexer allow the data of the ALU result to pass and do not allow the data of the read data to pass. And actually the data or the data flowing on this line are unknown to us because we did not perform any memory operation, so it's definitely invalid or wrong data, and I need the result of the addition operation, the addition of the value of RS to our immediate value. I wanted to pass it to the write back stage, and this multiplexer is the write back stage beginning, or the beginning of the write back stage. Okay, so here we did not perform anything in the memory access. We moved on to the write back stage. Starting from this multiplexer, we'll choose which data to be written or to be passed, and as you can see in the write back, we access the register file. So here we will have this data coming from this multiplexer, as you can follow the line, will be entered to the register file in the write data label, and here we have the write register label, which tells me which register I will write the write data to. Here comes a problem that we do not know whether we want to write in the RT or the RD register, because as you can see in the instruction decode, we decoded the instruction into an RT and into an RD because it's a dummy data path. We did not know which instruction we are executing. But in the write back stage, we exactly know which instruction we are executing, which is the add immediate. So do you believe the write register will be the number of register RT or the number of register RD, which actually does not exist, because I extracted bits from 11 to 15 from this instruction, which are useless to me. Bits from 11 to 15 alone are useless. They are actually part of the immediate. So guess what? This multiplexer acts as a gate and will allow the value of instruction 16 to 20, which is the register number of register RT, which will be our target register, to pass and become the write register. So our data will be stored in register RT. Okay, because this multiplexer passed the number of register RT, so it informed the register file that you need to store your data in this register, which is register RT. And here the value or the number of register RD is useless and is discarded because we are not performing an R-type instruction, we are performing an I-type instruction, and that's why this data to me is useless. It does not mean anything, and I only care about the register number of RT. Okay, so it's simple. In the write back, this multiplexer chose the value of the ALU result, and then it moved on to the register file. We have here a control signal called reg write or register write, which will inform the register file that we will write an operation. Okay, we want to write now to the register file, so this value should be 1, and this value comes from where? From the control signal, which we cannot see on this diagram definitely, but you will see it later on in the next tutorials and lectures. So it will write the value coming from the write data line to the register number specified in the write register line. Which write register number is specified? This multiplexer will choose the number of register RT and not this number, because we are an add immediate and I-type instruction, so I do not have a destination register, so this value is invalid. Okay, and this is actually the correct target or the correct register number. Okay, and definitely it will be chosen. The reg destination control signal is coming from where? Also from the control unit. As you can see, all blue lines here are data coming from the control unit, or they are control signals coming from the control unit. So anything is in blue here refers to the control unit, and these are control signals coming from the control unit. Okay, now we wrote our data. What actually happens is that we have some stages or some operations we skipped, so we can recall them fast now. For example, the program counter, we need to let the program counter or the PC point to the following or to the next instruction. So we perform PC plus 4 because we are byte addressable. So to move from one word to another, we need to add 4. Or to move from one instruction to another, we need to add 4, because one word equals 4 bytes. And each instruction consists of 4 bytes, or consists of a word or one word. So to move from a word to another, we add what? We add 4. So we have here this adder takes in the program counter value and the immediate value of 4, and then will result here in the PC plus 4. We will have that another adder, and as you recall from the previous tutorial, this adder calculates the branch address. Okay, it will always be calculated regardless of which instruction you are performing. Yes, it will try to take this immediate value and will try to add it to the program counter plus 4 and say this is my destination address that I need to jump to. But guess what? The data path became smarter with a control unit, and we have here a multiplexer that would allow the correct value of the PC to pass and update the PC register. So in an add immediate instruction, do you guess which value will pass? The PC plus 4, which is this line, or the PC plus 4 plus 5 multiplied by 4, because it tried to calculate a fictional branch address? As you all guessed correctly, it will allow the value of PC plus 4 alone to pass and will discard or ignore the value of the branch, because this is not a branch instruction. And this is controlled by the PC source control signal, which comes from where? As usual, the control unit. Okay? So now let's move on to a different example, which is the load word example. As you can see, the load word is an I format instruction. And as you can also see, load word T1, 4 and S1. S1 register is the register containing the base address, and 4 is the offset that I will add to this base address, meaning base address plus offset will result in the location I want to retrieve the data from. And this data retrieved will be saved or stored in register T1. Okay, so I'm having a base address and I'm having an offset. Okay, I will add this offset to the base address. It will result in the location I want to retrieve the data from. This data will be retrieved since it's a load word instruction, and load word means I will retrieve an entire word, which is 4 bytes, which is 32 bits. And this word will be stored in register T1. As you can see, the I type contains an opcode, an RS, an RT, and an immediate, exactly like the add immediate instruction. It is the same format. Add immediate, load word, store word, and branch unequal, all are I format instructions sharing the same format. So the difference, or it's a terminology difference, that we do not call bits from 0 to 15 immediate in load word and store word and branch unequal. We call them the offset, because they are going to be added to an address, so they are an offset. Okay, but other than that, everything is the same. So let's see how to decode this instruction and transform it from assembly to machine code. If you can see, load word has an opcode of 35, which is in binary 100011. Okay, it's already 6 bits, so I do not need to add any zeros to the left. Then we have register RS. RS in the load word and the store word is always the register containing the base address. So register S1 is register RS, and S1 is register 17, which is 10001 in binary. It's already 5 bits, so it will fit in the field. Register RT in this case will be the target register where I will store my retrieved data from the memory, which is register T1, which is register number 9, and converting 9 from decimal to binary, it is 1001. It's 4 bits, so I need to make it 5 bits. So what shall I do? I add a 0 to the left. So that's why it is 01001 to fit in the 5 bits required for this field, or the RT field. Finally, we have the offset, which is number 4 or decimal 4. Converting 4 into binary will be 100, but since the immediate or offset field takes 16 bits, I need to extend it to the left by 0. So I will add 13 zeros to the left. Okay? Now we will have this instruction. 100011 indicates I'm a load word. RS 10001 indicates I'm register S1. RT 01001 indicates I'm register T1. And finally, this value 13 zeros, then 100 indicates my immediate or offset is 4. This value will be concatenated and will be the equivalent machine code or binary code to this assembly instruction. So now let's move on to our lovely data path. As you can see here above in the blue box, we have the machine code instruction, which is the concatenation of the binary values of all fields. And let's start with our first stage, which is the instruction fetch stage. As you can see in this example, I will go quickly. since in the previous example and in the previous tutorial, I discussed the data path in details while stating the different stages the instruction will pass by. In this example, I will directly go to the different stages without explaining a lot of details. So let's start with the program counter. In the instruction fetch, which is stage 1, the program counter contains the address of the instruction I want to execute or the address of the next or following instruction, which will be this instruction. So the program counter will tell me the location of this instruction in the instruction memory. I will go to the instruction memory and retrieve or get this instruction, or formally state, or we can say it as fetching the instruction. So fetching the instruction means I will get this instruction from the instruction memory, and this is the end of the instruction fetch stage. Let's start with the instruction decode stage, and as you can see, we are in a dummy data path, so I will try to decode this instruction into all multiple formats R, I, and J. So here we have bits from 21 to 25 will contain the value of 10001, which is RS. Here bits from 16 to 20 will contain the value of 01001, which is the value of RT. Here we will have bits from 11 to 15, which should be RD in an R-type format, but guess what? It's a dummy data path. It does not know that we are executing an I, not an R, so it will try to retrieve a fictional RD value, which will be bits from 11 to 15, which are 00000, which are part of the immediate or offset, as you can see, so they are useless. And finally, we have here instruction from 0 to 15. We got our offset value, which is 4. It is extracted here. So the instruction decode will try to create all different combinations to satisfy all of our formats, because it does not know yet which instruction we are executing. That's the first part of the instruction decode. The second part is doing the sign extend and retrieving the values from the register file. So here we have the register file. Read register 1, we will try to retrieve the value of register RS. This number represents the number of register RS. This number will enter to the register file, and I will get the value inside register RS and output it into this line called read data 1. Okay? Also, I will try to read the data of register RT. Although in an I format, I do not care about the value of RT. But guess what? As usual, it's a dummy data path, so I will try to get the data of register RT. So read register 2 contains the number of register RT, and read data 2 contains the value inside this register, or the value inside the RT register, and it will be outputted on this line. And as we all know, later on in the data path, this value will be omitted or will not continue throughout the rest of the stages, because one of the multiplexers will stop it and will not allow it to pass. Okay, here the sign extend, we have this 16-bit value offset. We'll try to extend it into 32 bits. If we can see, the most common bit is 0, meaning it is a positive number, so I will add 16 bits or 16 zeros to the left. That's how the sign extend works. Okay, and now we finished what? We finished the instruction decode and register file read stage, which is stage 2. I decoded the instruction into all possible formats, and I got the values of registers RS and RT from the register file, although I do not need the value of register RT, but it's a dummy data path, so I will always retrieve the value of register RT, and it will be omitted in the following stages by one of the multiplexers. We move on into which stage? The execute stage. Now, what will we perform in the execute stage if our instruction is a load word instruction? You can guess it, and I'm pretty sure you guys are so smart that you will guess it correctly. We will perform the addition of the base address to the offset inside the ALU. So yes, we have an arithmetic operation we need to perform, which is adding the value of the base address to the offset. The value of the base address is where in register RS. So read data 1, which contains the value of RS, containing what? The value of the base address. So it will be an input to our arithmetic logic unit or ALU, and the second input, will it be the value of RT or the value of our offset or immediate sign extended? Definitely, guys are also smart and you will know that in a load word instruction, this multiplexer will allow the offset data to pass and will reject the value of RT to pass. Because why do you need the value of RT? You are not performing an R type, it's an I type instruction. The value of RT is useless, so this multiplexer with its control signal ALU source that came from the control unit will allow the value of the sign extend, which is the offset, to pass. So the ALU source will have value of 1 meaning the second line will pass, which is from the offset or the immediate. And in this ALU will perform the addition of the base address plus the offset, so we can have a target address to go to the memory with. As you can see here, we have the ALU control. The ALU control has an input control signal called ALU operation from the control unit. This ALU operation will tell the ALU control you need to inform the ALU module to perform an addition. I want to add the base address to the offset. So to perform an addition, the ALU control must tell the ALU to perform an addition. How will the ALU control know that actually we need to perform an addition? From the ALU operation control signal. And since it's an I-type instruction and all I-type instructions have unique opcodes, so the ALU operation control signal is enough to inform the ALU control that we need to perform an addition operation. So yes, the ALU control will tell the ALU perform an addition, and then it will add the base address to what? To the offset. The results will be the 0 flag. If the result of the arithmetic logic unit is 0, the 0 flag will be 1. Otherwise, the 0 flag will be 0. And here we have the ALU result, which will be the base address plus the offset. And that's the end of what? The execute stage. Here we have a memory access stage. I mean, we always have a memory access stage, but actually an operation will occur inside the memory in this instruction. Because we are performing a load word instruction, so we need to retrieve data from the data memory. As you can see here, the ALU result will pass directly to this multiplexer, and at the same time it will enter the data memory as an address. So this will be the address that I want to get the data from. We have here memory write and memory read signals. Which signal of these two signals will be one? Definitely the mem read, because it's a load word instruction, so we want to read data from the memory or from the data memory. Therefore, the mem read will be 1, the mem write will be 0. I do not want to write, I only want to read. So once this flag is 1, and this flag comes from where? The control unit, it will allow the memory to read data and output correct read data from the data memory on the read data line. So this line will contain the value I want to read, and then we will have this multiplexer, which is the beginning of the write back stage. And as you can see, this multiplexer will allow only one value to pass, whether the read data value or the ALU result. In this situation, in a load word instruction, do we need the ALU result? Do we need to store the base address plus offset in a register? No. What I care about is what the loaded value from the data memory, and that's why the mem2reg control signal will allow the read data to be passed to the next stage, which is the write back stage, and will reject the ALU result data to pass by. So as you can see, this multiplexer will choose which value, the read data, the data that we read from where? From the data memory. So the ALU calculated the base address plus offset. This is the location I want to retrieve data from the data memory. This will be input to the data memory as an address, okay? And then when the mem read signal is 1, I will read the data inside this address and output it onto the read data line. This multiplexer will then choose the read data line to go through the next stage, which is what? The write back stage, where we will write our loaded data to one of our registers. So we have here write data that will contain the read data or the data that we read from the data memory. It will continue moving on to this line till it reaches the write data of the register file. The reg write signal will be 1, indicating that we will write data to our register file. And finally, we have this multiplexer, which will tell us which register we want to store the value in. Will we store it in register RT or RD? Since we are an I type, we do not have actually an RD. So this value is useless, and therefore it will choose instruction from 16 to 20 to be the target register, to be the register that I will store my loaded data from the memory to. So this multiplexer with this control signal will allow this number to pass by to be the right register number, and then when the reg write value is 1, the value in the right data will be stored in the register specified on the right register line, which will be RT. And definitely we have the secondary operations, like for example updating the program counter to point to the following or next instruction. As you all know, PC plus 4, definitely this multiplexer will not allow the branch calculated address to pass, because this is not a branch unequal or a branch not equal instruction. This is a load word instruction. So actually calculating the branch address was not a correct decision, or the value calculated here is useless to us. So this multiplexer will allow the program counter plus 4 to pass by and update the current program counter register with the new value of the program counter to point to the next or the following instruction. Now we finished this example. Let's move on to our last example, which is the store word example. Okay, I told you I format has 4 important instructions: add immediate, load word, store word, and branch on equal. We will not tackle branch on equal this tutorial, but we will tackle add immediate, load word, and store word. We already tackled the add immediate and load word, and now we are tackling the store word. And as you can see, which I just stated, store word is an I format instruction. We have here store word, T1, 4, and S1. It is like exactly the load word instruction. The S1 acts as the base address, 4 here is the offset which I will add to the base address, but the difference is that T1 is the value I want to store to this location. So store word, I want to store some data to the memory. How do I store some data to the memory? First, I need to know the location, which address I want to store the data to, which is calculated here, base address plus offset. The second important info is the data I want to store, which exists inside register T1. So the value inside T1 will be stored in the base address plus offset value, or location or address. Okay, definitely the I type has an opcode 6 bits, RS 5 bits, RT 5 bits, and an immediate 16 bits, but in store word we call it an offset and not an immediate. Now let's decode and transform this assembly instruction into what? Into machine code or binary zeros and ones. The store word opcode is 43. You can get it from the table that will be given in the exam. 43 in binary is 101011. It is actually 6 bits, so I do not need to extend zeros to the left because it will fill in all 6 bits of the opcode. Now we have what? The RS. The RS register is the base address register, which is S1. S1 is the register number 17, which is 10001. It is actually 5 bits, so it will fill in all 5 bits of the RS field. Now register RT, which is T1, which is register number 9. T1 contains the value I want to store to the memory. So it is converted to binary to 1001. As I told you millions of times that 1001 is 4 bits and the RT field takes 5 bits. So I need to extend 1 bit to the left and it will be 0 to preserve the sign. Okay? Or to preserve the value actually. Because here we do not care about signs when it comes to translating from decimal to binary for the decode stage. Finally, here we have the offset, which is 4. 4 translated into binary is 100. It is 3 bits, but the field takes what? Takes 16 bits. So I need to extend 13 bits to the left and all will be zeros. Okay, so we will have this instruction. 101011 means we are store word. This is unique opcode. The RS is 10001, which indicates register S1. The RT is 01001, which indicates register T1, and finally the immediate is 13 zeros followed by 100, which indicates an offset of 4 or a constant number of 4. So how will this instruction flow in our data path? As you can see above, as usual, the blue box contains the concatenated instruction after concatenating the binary numbers together in the correct order and the correct format. Let's start with what our first stage, which is the instruction fetch stage. As usual, we have the program counter pointing to the next instruction I want to execute, and in this case I want to execute this store word instruction, so it contains the address of this store word instruction in the instruction memory. Now I will fetch this instruction or retrieve or get it from the instruction memory. This is the instruction fetch stage. The program counter points to the instruction I want to execute. I will retrieve this instruction or fetch this instruction from the instruction memory. So I will have 32 bits. I got the correct instruction from the instruction memory. This is the instruction fetch stage, which is also known as the IF stage. It's an abbreviation. We move on to the next stage, which is the instruction decode stage. As you can see, our dummy data path divided the instruction into all possible formats, R, I, and J. As you can see, this diagram only supports R and I. It does not support J yet, because this is a simple implementation. We have here instruction from 21 to 25, which is RS1001, which is this value. We got here instruction from 16 or bits from 16 to 20, which is RT01001, which is RT value. Here we have instruction from 11 to 15, which is 00000. 11 to 15 is part of the immediate, but since it's a dummy data path, it does not know what instruction I am executing currently. In the instruction decode, it will know later on, starting from the execute stage, but in the instruction decode, it does not know what instruction I am executing, and therefore it tried to map it to an RD or a destination register or an R-type instruction, but guess what? This value will have no importance. It is useless. It will not be used throughout the data path. And finally, we have here instruction from 0 to 15, which contains our immediate or our offset value, which is 4. This is the first step of the instruction decode. The second step of the instruction decode is to actually get the values from the register file. So as you can see, we will always retrieve the value of register RS, which is read register 1. So we will try to retrieve the value of RS and output it on line read data 1. And since we are a store word instruction, actually the value of register RT is very important to us. I mean, in cases of the load word and the add immediate, I did not care about the value of register RT because it was acting as a target register. I will save data to it. But in store word, it does not act as a target register. Actually, it contains the data I want to store to the data memory in case of a store word. So the value of RT is important to me. And even if it is a dummy data path, but it is somehow smart that it always calculates the value of RT regardless, or it actually always retrieves the value of RT regardless of what instruction you are performing. Because not all I format instructions neglect the value of RT. The store instructions, store word and store byte and whatever store instructions actually use the value of RT to store it in the data memory. So here at read register 2 line, we have the register number of RT, and in the register file we will retrieve the data or the value of register RT and output it in read data 2. So in read data 1, we got the value of register RS, which contains the base address. On read data 2, we retrieved the value of register RT, which contains the data we want to store to the data memory. Okay, and we here have the sign extend modules, module which takes the immediate value and extends it from 16 bits to 32 bits. It's a sign extend, so if the sign is positive, which here it is positive, which is the sign bit is 0, so I will extend the value or the number by 16 zeros to the left and will be output to the sign extend module. So I transformed a number from 16 bits, or I extended this immediate value from 16 bits to 32 bits by duplicating the sign bit 16 times. Okay, and this is the end of the instruction decode stage, which we call it the ID stage. Okay, the ID stage. Let's move on to the execute or EX stage. In the execute stage, we have the arithmetic logic unit, or the ALU, which will perform an arithmetic operation. In a store word instruction, which arithmetic operation do we want to perform? We want to perform the addition of the base address to the offset to calculate the location or the address I want to store my data to. Okay, so I have an address that I want to store the data to the memory. This address is calculated by base address plus offset. So as you can see, the first input to the ALU module or the ALU unit is the value of register RS, which is the base address. The second value or input value to the ALU will be what? Will be the value of register RT, which contains the data I want to store to the data memory, or will be the immediate or offset I got from the sign extend module. As you all guessed correctly, I want to add base address plus offset. So this multiplexer will act as a gate, and it will not allow the value of register RT to pass to the ALU, but it will allow the value of the sign extend, which contains the offset I want to add to the base address, to pass to the ALU. So this ALU will perform the operation of base address plus offset. And this multiplexer, it has the control signal ALU source, which was gotten from the control unit. As you can remember, in the instruction decode, we have a control unit that takes the opcode bits from 26 to 31, these bits, and enters to the control unit, and then the control unit will output all control signals in the data path. And control signals are marked by blue labels. So all blue labels are the control signals output from the control unit, which includes the ALU source. So the ALU source knows that it's a store word instruction. I want to perform base address plus offset, so I will allow the value of the sign extend, which is the offset, to pass to the ALU and prevent the value of RT, which is the data I want to store to the data memory, to pass to the ALU. This data may pass to other stages or to other components, but it will not be an input to what? To the ALU. And as you can remember, we have here the ALU control, which informs or tells the ALU which operation to perform. Should I perform an addition, a subtraction, ORing, ANDing, whatever. Okay, and the ALU control has two inputs: the ALU operation, which is a signal from the control unit, and bits from 0 to 5 from the instruction, which in case of an R-type instruction, these are the function bits, the 6 bits that represent the function. Okay, it's a dummy data path, so always bits from 0 to 5 will pass or will be input to the ALU control, regardless of whether we are performing an R, an I, or a J instruction execution. Okay, but according to the ALU operation, which is from the control unit, whether I will use these bits to determine which operation the ALU should perform, or I will neglect these bits, and actually the ALU operation knows exactly what operation should be performed in the ALU and will tell the ALU control to inform the ALU about the operation. So in our case, it's a store word instruction. A store word has a unique opcode since it's an I-type format, so the ALU operation signal or control signal is enough to inform the ALU control that the ALU needs to perform an addition operation of the base address plus offset. I do not need bits from 0 to 5 because they are useless in case of an I-type instruction. I mean, bits from 0 to 5 are part of the immediate, which are useless. We are not an R-type, it's an I-type. So do not use these bits to determine which instruction the ALU or which operation the ALU to perform, which arithmetic operation. No, as an ALU operation control signal, since this instruction has a unique opcode, so I 100% know what operation the ALU should perform. So the ALU operation control signal will tell the ALU control which operations the ALU must perform. In our case, it will be an addition. Okay, and then we will have our result coming out from the ALU result line. The ALU result contains the base address plus offset, and here we have the 0 flag. It's a 1-bit flag indicating whether the result of the ALU was 0 or not. If the result of the ALU, which was base address plus offset, was 0, the 0 flag will be 1. Otherwise, if the result was not 0, the 0 flag will be 0. The ALU result can go into two directions, whether as an input to our data memory or to the multiplexer. Okay, if it is an input to the data memory, it will be as an address, and if it is input to the multiplexer, it means that I want to store this value in one of my registers. Okay, but as you all know, this multiplexer will allow only one value to pass from both values. So moving on to the memory stage, which is the mem stage, MEM, we can see that in a store word instruction we want to write to the data memory. So the mem write signal should be 1 and the mem read signal should be 0. And I cannot have both signals 1 at the same time. I cannot read and write at the same time or at the same clock cycle. It is impossible. That's why if I'm a store word instruction, the control unit will tell the mem write to be 1 and will tell the mem read to be 0. And I have here as an input the ALU result, which is base address plus offset, which is the address or the location I want to store the data in. So I have some data and I want to store it in the data memory. Okay, I need to have the address or the location where to store this data. And this location was calculated in the ALU by base address plus offset. Okay, so using this address, it is my location that I will store the data in. Now I need to know where is the data that I need to store. The data was the value of register RT, and as you can see, read data 2 contained the value of register RT. You can see here we have a connection or a line going directly to the data memory called write data. This write data is containing the data to be written to the data memory. So the value of register RT will flow in this line, and if the memory write or mem write signal is 1, this data present in the write data will be written or stored or saved in the location specified by the address, which is the ALU result. Okay, and then I will finish my instruction. We will have a write back instruction. Yes, guess what? We will have a write back instruction. Now, a question you guys should ask. In this instruction, it's a store word. I did not load any data from the memory, so the read data line has unknown data, invalid values, and actually the ALU result was containing or having the base address plus offset. And I do not want to store the base address plus offset into any register, because the store word instruction stops when I store my data, the value of RT, to the address specified in the instruction. So this multiplexer will select which value. If you recall your hardware courses, you remember the X, the don't care value. The control unit will initialize or send data to mem to reg. The mem to reg signal will be don't care. It will be an X, meaning select whatever data. Select the data from the read data or select the data from the ALU result. Okay? Okay, we will select this data. And since we are a 5-stage, we need to perform the write back stage. Even if I'm not performing any operation on the register file, but I need to pass by the write back stage. Like when we had an add instruction and we passed by the memory stage, although we never accessed the memory. Same will occur in the write back stage. I will not access the register file. So a random data from both lines will be passed because the signal was don't care, and it will be added here to the write data. This multiplexer will have its signal as don't care 2 because I do not have a destination register. So I do not care about selecting one of both values or one of both registers because I will not actually write any data to the register file. How can I prevent the register file from writing? That's the answer. The reg write signal. The reg write signal, as long as it is 0, nothing will be written to the register file. If the reg write is 1, I will write to the register file. That's why I did not care about the value this multiplexer chose, and I did not care about the value this multiplexer chose, because guess what? I do not care about write data or the number of the register or the write register number. Why? Because the reg write signal will be 0. Since it's a store word instruction, I am not writing to the register file, so this control signal will be 0. Therefore, I will not write any data to my register file. So I do not care which data you selected or which register number you selected. Select whatever you want. At the end of the day, I will not write anything to the register file, because my register file is what? My register write signal is 0. Okay? And as you can see, we have some secondary operations like updating the program counter by 4 to point to the next instruction. And this multiplexer will not select the branch address calculation. It will select what? The PC plus 4, because it's a store word. So I am going to execute the sequential, or I'm going to execute my instructions in sequence, because it's not a branch instruction. So I will not branch to any other address. Okay? So now let's move on to some theoretical questions. Our first question was, why is the sign extend module needed in the MIPS Datapath simple implementation? So if you can remember, we had here the sign extend, and I'm pretty sure I stated the functionality of the sign extend multiple times. Why do we need sign extend? Because the immediate or offset value coming from the instruction is 16 bits, and all of our data and register values are 32 bits. So to perform any operation inside the ALU, I need to have compatible widths. Both input parameters or input values to the ALU must be the same widths, 32 and 32. And if the value of RS here, for example, is 32 bits, then I need to have the value of the immediate or offset 32 bits too. So I need to extend this value. How to extend this value? Using a sign extend module. And since it's a sign extend module, so it takes into consideration the sign of the value. Okay, whether it is positive or negative. The sign is the most significant bit, which is bit number 15. So if bit number 15 is 0, it means the number is positive. So I need to add 16 zeros to the left. If bit number 15 is 1, it means the number is negative. I need to add 16 ones to the left. Okay, and thus the number became what? Became compatible, having the same widths as all of our data in our MIPS architecture, which are 32 bits in width or in size. Okay, now question 2 tells us, imagine instructions with the following offsets or following immediate numbers. What is the output of the sign extend module? As you can see, number A, bit number 15 is 1 or 0? It is 1, meaning it's a negative number. So I need to extend this number by how much? By 16 ones to the left. So you can see here, I add 16 ones to the left to this number. The second number, B, the most significant bit or bit number 15 is what? Is 0. It means the number is positive. So I need to add 16 zeros to the left. So as you can see, we added 16 zeros to the left, and then this is the rest of the number. And this is the output of a sign extend module, and you need to know how does it actually operates. So it duplicates the sign bit 16 times to the left. So now let's move on to the next question, and question 3. What does the address field in the jump instruction represent? If you recall, the jump instruction belongs to the J format. And if you remember the J format, we have two fields only. We have the opcode field, bits from 26 to 31, which means it's 6 bits as usual. And we have another field, which is the address field, which consists of bits from 0 to 26. And in the question, we are asking, what does the address field represent? If we break down the jump instruction more, we will find out that the jump instruction opcode is value or decimal value 2, which is in binary 000010, because the opcode is 6 bits. So even if 2 can be represented only in 2 bits, we need to extend to fill in all 6 bits of the opcode. That's why we added 4 zeros to the left. Okay, we can find here bits from 0 to 25, which are 26 bits containing the address. And now a question might appear. The question is, how can we represent an address in 26 bits although all of our addresses are 32 bits. If you remember, we told you in the MIPS architecture, the register size is 32 bits, the data memory size and the instruction memory size, or the memory in general, if it's a von Neumann memory, is 32 bits in width, and the addresses which point to the memory are 32 bits. So how can I represent a 32-bit address in 26 bits? This is the answer. The 26-bit field in jump instructions is a word address, meaning that it represents a 28-bit byte address. So what happens is that this address field does not actually contain the byte address. It contains a word address. And if you remember, words are 0, 1, 2, 3, but bytes are 0, 4, 8, and 12. Because one word is equal to 4 bytes, so to move from one word to another, we need to add 4. And our memory, or all of our addresses in the MIPS architecture, are byte addressable, or are byte addresses, meaning that they point to bytes. They do not point to words. They point to bytes. And that's why to move from a word to another, I need to jump by 4. Like if you remember the program counter, when we incremented the program counter by 4, because the program counter contains the address of an instruction, and to move on to the next instruction, I need to point to the next word, and to move from one word to another, I need to increment by 4. The same here. This address field does not contain a byte address. It contains a word. For example, word 0, word 1, word 2. Okay? Thus, to transform a word address to a byte address, what did we perform? We multiply by 4. If you remember the branch, and that's the difference. The branch instruction, when we try to calculate the branch address, or make the branch address calculation in the execute stage, we told you that we have the immediate or the offset, and we need to multiply this by how much? By 4. Because it was a word offset. It was not a byte offset. It did not tell me how many bytes I need to skip or move. It told me how many words I need to move. Thus, we had to transform this word offset into a byte offset by multiplying by 4. Same occurs here, but the only difference between the jump and the branch unequal, or the branch instructions, is the branch instructions had an offset. This offset was not an address. It was a value that I will add to the program counter to move. Okay, so it is relative to the program counter. For example, if the branch unequal offset was 2, this means I need to move 2 words from the current program counter, or from the next program counter if it is PC plus 4, which is always PC plus 4. So it means I need to move plus 2 words from the PC plus 4. So this offset value, it's called an offset because it was added to an address. Here in the jump instruction, this value is not added anywhere. This is the actual address. It's the obsolete address, okay? We will not add this value to anything. This should be the 32-bit address. Not like the offset in the branch where we added it to what? To the program counter to know how many steps I need to jump, how many words I need to jump. The only common thing between the jump and the branch is that they provide words, okay? The offset in the branch is a word offset, and the address in the jump instruction is a word address. It is not a byte address. So in both scenarios, I need to multiply by 4. Okay? So actually multiplying a word by 4, meaning it will shift it to the left by 2. So shifting to the left by 2, meaning I will add at the end of the day 2 zeros to the right. Alright, so bit 0 and bit 1 will be 2 zeros because I'm doing a shift left logic. So multiplying by 4 or shifting to the left by 2 will add 2 zeros to the right. Okay, so at the end, this address field is a word address, it is not a byte address. Okay, we need to multiply it by 4 to have our byte address. Okay, just for here, you should know that this address is a word address, and to convert it into a byte address, as usual, we need to multiply by 4 or shift to the left by 2. Question 4. To what instruction seen in class the jump looks like? and what is the main difference between the two. As I told you before, the jump looks like a branch instruction, but it is not conditional. Meaning what? The branch on equal instruction, I am checking if T1 is equal T2, I will jump to this label. It's a conditional jump. While the normal jump instruction is unconditional or not conditional. It will always jump to this label. J label 1 will always jump to label 1. There are no conditions. Unlike the branch on equal and the branch not equal at all of the branch family, where I perform a condition, and if the condition is true, I will jump. Otherwise, if the condition is false, I will not jump. So that's the main difference. Branch on equal or branch is conditional, the jumps are unconditional. Okay, the jump and the jump and link, for example, and the jump register too. But as I told you, or as you can remember, the jump register is an R format, while the jump and the jump and link are J formats. Now, in the jump instruction, which is question 5, in the jump instruction, the effective target address is in the current 256 MB region. How is the destination address for a jump instruction formed? And a hint, the low order 2 bits of a jump address are always 00, which is base 2, which is binary. So basically, this question 5, is trying to ask us how do we transform the 26-bit or the 26 bits present in the address field into an actual 32-bit address that I can jump to. So, as you can remember, this is the jump instruction, this is the opcode, and this is the address. And we told you this address is a word address. Okay? So what happens? The 26 bits are here. So let's assume this box has the 26 bits. Okay? To transform from a word address to a byte address, we do what? We multiply by 4 or we shift to the left by 2. Multiplying by 4 or shifting to the left by 2 will add 2 zeros to the right, as I told you before. So actually I will have the 26 bits and I will add 2 zeros to the right. So I will have 26 bits and 2 zeros. The total will be how much? 28 bits. So the first step is transforming our word address into a byte address, meaning I will transform it from 26 bits into 28 bits by adding 2 zeros to the right. What is the logical operation we did to add 2 zeros to the right? We multiplied by 4 or shift to the left by 2 without removing any bits from the 26 bits. It's very important. We did not cut any bits. We kept the 26 bits, but we added 2 zeros to the right. Okay? Now, the last step is, now I have a 28-bit. I mean, this box from this line till the end of the 2 zeros, we have 28 bits. There are 4 bits missing to form what? To form a 32-bit address. How to form a 32-bit address? If I have the program counter, okay, this is the normal program counter. I will take the most significant 4 bits and add them to be the most significant 4 bits of our address. Listen carefully. I have the program counter, which is 32 bits. I will take the most significant 4 bits, okay, which are bit 28, bit 29, bit 30, and bit 31. These are the 4 most significant bits in our program counter, and I will add them or put them or concatenate them to my 28-bit address. So adding 28 plus 4 will result in a 32-bit address. So bit 28 in the program counter will become bit 28 in our address. Bit 29 in the program counter will become bit 29 in our address. Bit 30 in our program counter will become bit 30 in the address, and finally bit 31 in the program counter will become bit 31 in our address. So as you can see here, the most significant 4 bits are moved up to here, or are copied and are concatenated to the address. So now we have a 32-bit address, and then this address, the 32 bits, will update the program counter, or the program counter will be updated with these 32 bits. So as a summary, we have a 26-bit address, which is a word address, not a byte address, which is these 26 bits. To convert it from a word address to a byte address, or to convert these 26 bits to a 32-bit address, the first step we do is to add 2 zeros to the right, which is like shifting to the left by 2. Without removing any bits, we are preserving all 26 bits, but we will add 2 zeros to the right. Okay? After adding 2 zeros to the right, we'll have from 26 bits to 28 bits. Now we have a 28-bit address. We need to make it 32 bits. So we take the most significant 4 bits from the program counter or the PC and add them to be the most significant 4 bits in our 28-bit address. Adding 4 bits to 28 bits will result in 32 bits. This will be our final address, which we will update the program counter with. The program counter will be updated with this address so to perform the jump operation. We have here a simple example, which is we have this jump instruction. Imagine we had a jump instruction, and this is its equivalent machine code or binary zeros and ones. Okay, we have the first most significant 6 bits are the opcode, which is 000010. This is a decimal value 2, which indicates this instruction is a jump instruction. Therefore, the rest of the 26 or the rest of the 32 bits, which are 26 bits, are the word address. We need to transform this word address into what? Into a byte address. So the 26-bit target field from the jump instruction, this 26 bits will move to be here. Okay? And then we will add or shift left 2 positions to add 2 zeros to the right. So we took this number and we added 2 zeros to the right, which are the blue zeros. The last step is what? To take the high order 4 bits from the program counter, or to take the most significant 4 bits from the program counter and concatenate them to our address, so to have a 32-bit address. So we had this jump instruction. The address field had 26 bits. We took these 26 bits in black and added them to the jump address, the location I want to jump to, but I need to transform it from 26 bits to 32 bits. So since it was a word address, I need to convert it to a byte address by adding 2 zeros to the right, which are these 2 blue zeros. Then in this operation, we moved from 26 bits to 28 bits. There are 4 bits remaining to have a 32-bit address. From where do we get these remaining 4 bits? They are the most significant 4 bits from the program counter, or the high order 4 bits from the PC. We will add them as the most significant 4 bits to our address, and thus we will have a 32-bit address. Okay, it's a designer choice. The designers of the MIPS architecture decided to make it like this. Have a 26-bit address, which is a word address, first converted to a byte address by adding 2 zeros to the right, which is multiplying by 4 or shifting left 2 positions. Now we have 28-bit address. Still there are 4 bits remaining to create a 32-bit address. From where do we get the remaining 4 bits? They are the most significant 4 bits of the program counter. We'll have a copy from them and concatenate them to be the most significant 4 bits of our jump address, and this entire address will become the address I want to jump to. Now I am done. If you have any question, don't hesitate to post it on Piazza, and one of the course instructors will reply to you. Good luck and see you soon.